Imagine a material so frustrated by its own geometry that it can't settle into a single, stable pattern, yet still holds deep, hidden order. Not chaos, not randomness, but a kind of intelligent disorder. This isn't fantasy. It's kagome spin ice, a playground of emergent physics where magnetic spins obey local rules, but global frustration leads to exotic states that defy classical intuition. And today we're going to explore how artificial intelligence, specifically, a type of neural network called a restricted Boltzmann machine, is helping physicists see the invisible. At the heart of this system is a simple rule. On every triangle, two spins must point inward, one outward, or vice versa. This is the ice rule, inspired by the hydrogen bonding patterns in real water ice. But here the spins aren't atoms, they're quantum magnetic moments, like microscopic compass needles. Now imagine a lattice made entirely of such triangles, sharing edges. The number of ways to satisfy the ice rule across the entire system. It grows exponentially with size. We're not talking about a few configurations. We're talking about billions upon billions, each one equally valid. This is extensive degeneracy. And when you have that many ground states, even at absolute zero, you get residual entropy, a measure of disorder that refuses to vanish. That's not a flaw in the system. It's a feature. It's the fingerprint of frustration. But here's the twist. Even though the spins look disordered, they're not independent. There are subtle short-range correlations. A spin's orientation influences its neighbors, but only within a few lattice steps. Beyond that, the pattern fades. No long-range order. No symmetry breaking. Just a persistent, fluctuating memory of the rules. This is the ice-eye phase, a classical spin liquid. A state that behaves like a liquid, not because it's hot, but because it's frustrated. The system can't choose one configuration over another. It dances between them all. So how do we model something like this? Traditional methods, like solving the Hamiltonian exactly, fail when the number of states explodes. But enter the Restricted Boltzmann Machine, or RBM, a generative model that doesn't need to know the rules in advance. Think of it as a statistical detective. You feed it thousands of spin configurations generated by Monte Carlo simulations, snapshots of the system in different possible states. The RBM doesn't memorize them. Instead, it learns the probability distribution that governs them. It does this by adjusting the weights between visible spins and hidden neurons, learning which combinations are likely, which are rare, and how spins correlate across space. And when researchers trained an RBM on the ice-eye phase, something remarkable happened. The model didn't just mimic the data. It reproduced the physics. The spin-spin correlation function, how likely two spins are to align based on distance. The RBM matched it exactly. Even more telling, the decay was exponential, signaling short-range order, just like in the real system. But here's the deeper insight. The RBM learned the constraints. It encoded the rule that 3 spins in a row can't all be the same. Not because it was told, but because the data told it. The network internalized the ice rule as a pattern in its weights. Now let's turn up the complexity. Add long-range dipolar interactions, like magnetic charges repelling each other. Suddenly, the system wants to minimize energy not just locally, but globally. And so the defects, those triangles that break the ice rule, start to organize. The +3 and -3 charges form a staggered pattern, like a magnetic checkerboard. This is the ice-eye phase. It's a new kind of order, not in the spins themselves, but in the emergent magnetic monopoles. These aren't real particles. They're quasi-particles, effective charges that arise from the violation of the ice rule. But they're real enough to interact, to move, to form bound states. And the physics changes dramatically. The correlation function no longer decays exponentially. Instead, it follows a power law, 1/r². That's a signature of algebraic correlations, long-range influence without true long-range order. This is the hallmark of a system with hidden long-range structure, a dimer-like arrangement, perhaps, or a hidden order parameter. But how do you capture that in a model? The RBM can still learn it, but only with a twist. For ice-eye, the model worked with just the weights. But for ice-eye, it needed a uniform bias field in the hidden layer. Why? Because the ice-eye phase breaks time reversal symmetry. Up and down are no longer equivalent. The system now prefers certain configurations, not because they're more likely in isolation, but because they minimize the energy of the monopole interactions. The bias field acts like a subtle nudge, a symmetry-breaking field that allows the RBM to capture this preference. It's not just learning the rules. It's learning the bias in the system. And when tested, the results were stunning. The RBM generated spin configurations that were statistically indistinguishable from the real ones. The correlation functions matched. The charge distributions matched. Even the weight distributions told a story. In ice-eye, the couplings were spread out, reflecting a fluctuating, degenerate system. In ice-eye, they clustered tightly, evidence of reduced entropy, increased regularity. This isn't just fitting data. This is physics discovery. So what does this mean? It means that machine learning isn't just a tool for prediction. It's becoming a new method of scientific inquiry, especially for systems where traditional theory fails. When frustration, degeneracy, and emergent phenomena collide, the math gets messy. Intuition breaks down. But the RBM doesn't need intuition. It learns from data. It finds the statistical structure behind the chaos. It discovers the hidden rules, rules that might take decades to uncover with pencil and paper. In the end, the most chaotic systems may be the ones that teach us the most. Because in their disorder, there's a language, a statistical grammar of spin, charge, and constraint. And now we're learning to speak it. With tools like RBMs, we're not just simulating quantum matter. We're decoding it. So the next time you see a complex pattern, whether in a material, a network, or even in data, ask yourself, what rules are hidden beneath? Because in the world of frustrated magnetism, the answer is no longer just, we don't know. It's we've taught a machine to find it.